presentation I'll read the title, How Xterra's Stirling Engine Can Use Waste Heat to Revolutionize Sustainable Electricity. So, the world is electrifying and we need to figure out as many sources as we can to get there. And some tidbits out of what was posted for the talk. Over 70% of the energy produced globally is lost as waste heat. So not just CO2 heating up the atmosphere, is it? So yeah, something else to think about. So this presentation will be how their Stirling engines can convert heat into electricity. This is a Brendan's with a startup, Xterra, that was developing these Stirling engine technologies since I believe 2019 is when he founded the company. And he is a professor at Ontario Tech University, or for those of us longer in the tooth, University of Ontario UOIT, whatever that was, stood for. So, anyway, without further ado, I think I've covered enough. We'll let Brendan fill in the gaps and over to you.
Thanks, David. Appreciate it. I'm just gonna set up you can see the screen okay?
Yes.
Awesome. Yeah, so David, you mostly covered it. Yeah, so I'm gonna be talking about Xterra's Stirling engine technology today. And I'm CEO at Xterra and co-founder, and also a professor at Ontario Tech in mechanical engineering is what my background is in. So yeah, first things first, I like to talk about the problem and then put in context where the opportunity really is here. So we're in need of energy sources, and a big player in this is the fact that right now we're essentially electrifying almost everything, right? So cars is the big example, but even when you look at things like steel mills, they're retiring their old blast furnaces, coal furnaces, and replacing them with electric arc furnaces now. So the grid is struggling to keep up with this demand right now. And we find ourselves looking around for are there more clean energy sources? And we're finding that the struggle is in having these be all three things: clean, affordable, and reliable. So the world right now is really desperate for new energy sources that can help us keep up with this increasing electrification demand. At the same time, 70% of the energy we produce globally is lost as waste heat. Okay. That is a massive amount of energy, right? So if we even take a small slice of that, that is an incredible amount of energy we're talking about. So tapping into that is something that's critically important. And this aligns really well too. So I've put this pie chart here of the global carbon dioxide emissions, and it's broken out. We have this difficult to eliminate emission section. And you can see among these ones that are difficult to eliminate, that tends to be because the technology is lacking to allow them to produce the products we need while reducing carbon emissions. And you see in here iron and steel, cement. I'll be talking a lot about those two today because they also have a lot of waste heat available that they're not currently able to use. So there's this really good match between, like, if they could capture some of this energy, they could also reduce their carbon emissions and save money at the same time. Load following electricity is another very interesting one. And that tends to be natural gas that we're bringing online to keep up with that electricity demand right now because it's easy to throttle. But we have other options too we could potentially do involving other kinds of waste or heat sources, sorry, like things like biomass, right? Again, tends to be a lack of technology to get that clean, affordable, and reliable. So we do have the ability to convert heat to power now. And I want to talk about that first because steam turbines is the most common technology for this. And what you see with steam and organic Rankine cycles, which is a newish technology that's similar to steam, is that those tend to have to be really large to be feasible, right? So they need to be large to be efficient and they need to be large to make economic sense. And so I've shown a picture there of like a generating station, what their steam turbine setup would look like. So generally it's on the size of a building. And we're talking like tends to be in the range of sort of at the bare minimum 10 megawatts, usually 20 megawatts or above to make these systems make sense. So below that is where a huge majority of these heat sources sit. And that's why we're not capitalizing on them now, because our current technology can't really get it done because they need to be so big and expensive. Another way to do heat to power is the Stirling engine. And that's what I want to focus on today in the talk. And so I'll give you a little bit of background on this technology. It's been around for 200 years. Okay. And so when I teach thermodynamics, I always start with this because the Stirling engine is the cycle with the highest possible efficiency, and it can use external heat sources. So that means it's not like internal combustion where you have to have a specific fuel. You can have literally any heat source, completely heat agnostic. The heat comes from outside the piston, and so you can convert any heat into power. And so the question is, okay, so if it's the best, right? Like if it's the most efficient and it's external, why don't we see these everywhere? And when you look around, if you tried to buy one now or you look into it, they tend to have efficiencies that are 20% max, which is way below the efficiency they should have. And they tend to run typically on fossil fuel sources. So you'll see them natural gas, butane, propane, things like that, which essentially has nullified all their advantages, right? And so it's really puzzling when you look at this, that this is what got us interested in it. There's this puzzle here to why we don't see Stirling engines more. They're such a great heat to power technology. And this encompasses it really well. So if you do a search online for Stirling engines, you'll come to this Bill Nye video where he talks about Stirling engines. He loves Stirling engines. And you can see the one he uses in his video looks very similar to the one I showed that was roughly 200 years old. And there hasn't been a lot of change, significant change within Stirling engine designs. And I won't read his quote, but I'll summarize it for you. You probably already read it. He says Stirling engines can make a big comeback because they're so efficient. And he says if we can get someone to figure out how to get these things to work, you can change the world. So there's a huge amount of potential if we can figure these things out. So now I would be teaching a class at Ontario Tech, a fourth year class called Applied Thermal and Fluids Engineering, where we teach the engine cycles. And I'd be telling my students, listen, and we always teach Stirling first, right? I was like, someone's got to figure this out. There's so much potential here. How are we not doing this? At this day and age, where we're looking for clean sources and there's all this heat available, we have to figure this out. This could be enormous, right? And enough times teaching that, it got to the point where what happened was I was on a trip to Bangladesh. That's what this picture shows. So I took this picture. We were walking through the countryside. So this is actually my grad student. We were staying with his family. And these are his family's rice fields we're walking through. And like to the mechanical engineer, I noticed this engine sitting in the middle of the field. And I'm like, what is going on there? So to grow rice, you got to keep it submerged in water. So what they do is they have this pump here to pull water from underground, and it's diesel powered. So it turns out they hire someone whose full-time job is to make sure that these fields stay flooded, and their full-time job is running this diesel engine in the middle of rural Bangladesh. And of course, it turns out their biggest cost to growing rice is the diesel to operate this pump. And it just struck me in that moment. I was like, this is crazy because there's so many heat sources available. Like it was 42 degrees that day. The sun was beaming down, so there's solar energy. There's all the crop waste, the agricultural waste from the growing of the rice. They use cow dung for cooking. There's just so much potential here that I was like, this is nuts. Like I gotta dive into this and figure out what's going on because if we could make something happen here, it's gonna be huge. So this is where the journey starts for me, right? So I jump in with both feet, and the first question is, why don't we have Stirling engines everywhere? Like, why are the past engines not living up to their potential? And we started as a research project, and I'll just sort of summarize these plots for you. Essentially, what you're looking at this plot here, the shaded area represents the work that you can get out from the engine. So this dashed line is what the Stirling cycle theoretically should be operating at, and this red area is what all the past designs that were sinusoidally limited, meaning they just have continual motion, right? That's where they can operate. So all this blue shaded area is work that they can never access. And that's what opened our eyes to what's happening. So essentially, in a nutshell, what had been done previously was they were just using the technology of the day, which worked well for internal combustion engines. And this is crankshafts that just spin continuously, right? It turns out when you try to apply that to external engines, you're losing a huge amount of efficiency. And that's what the plot on the right shows us here. So we've got efficiency plotted here. And this dashed line is what the Stirling cycle should be capable of, theoretically, right? If you operate sinusoidally, you now have a max efficiency that's capped at this solid dark red line here. And so we're talking about a 30% gap before you even start to operate your engine. Just because of your design, you're losing 30% right off the top. No matter how good of a job you do, you never get that back. And that was our really like, okay, this is interesting. Let's see if modern technology can start to address this. So we published a paper on that, moved on to the next sort of straightforward question that would follow from that. Can we follow the real Stirling cycle? Is it possible to live up to its potential by accessing that work, that efficiency that we're missing, right? And so I put this plot here again so I can side by side it with our data. So you can see from our data, we're able to follow the Stirling cycle more closely if we can just modify how it spins. So instead of spinning continuously, we design our own mechanism so that we can control the motion. Once we do that, we can start to access the true Stirling cycle performance and really get at the heart of like, how can it live up to its true potential? So again, still a research project, published a few papers on this, and then we start to ask the follow-up questions. And first I'll let you peek behind the curtain here and see. I want to show you sort of specifically what we're doing. And it's patented, so we're okay there. Essentially what we've done instead of a crankshaft is we've replaced it with this cam groove. And because of modern manufacturing technologies and the precision we have now and the control we have now, we can program this whatever curve we want. We can cut whatever shape we want on this curve. And this curve ultimately controls the motion of the displacer. So this shaft right here is connected to a displacer down here. And what that's doing is it's shifting its air between the hot side and the cold side. So if we start to have control over that, you can think of it almost like a software program. We can mechanically control this system and have a precise path that that displacer follows to mimic exactly what the Stirling cycle is expecting and get those really high efficiencies that we're supposed to have. The second technology was the regenerators. So in a Stirling engine, the regenerator is the technology that sits between the hot and the cold chamber. And as the gas moves between the hot side and the cold side, it stores that thermal energy. So each cycle, as the gas goes back and forth between hot side, cold side, hot side, cold side, the regenerators sit there and store all that energy. So you don't have to re-add that energy each cycle. And again, that's what lets it get those incredibly high efficiencies. So we've been applying modern technologies to this too. So we're using 3D printed metal parts, for example, to get, functionality that we've never had before, right? And this is what's opening the door to these much higher efficiencies that's going to let the Stirling engine, we think, come in and convert all this available waste heat that we've never been able to use before into electricity. And we have pending patents on that second technology. The granted patents are on the first technology. Okay, so this was the next step for us. Okay, we figured out why the past ones are so bad. We know we can make an engine that can follow the Stirling cycle. So now it's time to patent it. So this is our granted US patent. We have a number of other patents. I didn't show them all here. And we have the filed patents that I mentioned that haven't been granted yet. And we asked the question, how can we maximize our impact? So what I did at that point was look towards, can we commercialize this technology? And that's something that's really been close to my heart for a long time. So we joined the Brilliant Catalyst, which is the incubator that's out of Ontario Tech University. And phenomenal programming, right? To teach us how to grow a business, also to look at the market, right? Like you can imagine there are an enormous amount of applications for this. So we got to be careful in focusing in on where we think that early adopters are or that low-hanging fruit for these applications. And so that's me joining the Brilliant Catalyst, and we incorporated in 2019, and then we started to grow this as a business and look at what potential growth opportunities there were there. So this is what our benchtop prototype looks like. We've actually just wrapped up the testing on this. I'll let the video play here. And so what we essentially did here was to de-risk the technology. That's what they call it in the startup space. So we're de-risking the fact that we're the first time this has ever had, a displacer control mechanism. And so I'll let that play again. So we're controlling this here with a fairly simplistic curve. And at the bottom of this, we have a heat source. We're just using an electric heater that we crank up to about 500 or 550 degrees Celsius. And so you can see it's actually really impressive, this engine performance we're getting at such a low temperature. Most, gas engines will operate 1200 degrees Celsius or more. So the fact that we're at 500 is amazing because the efficiency and temperature are linked. I'll show you that again. And we can actually get this thing to run now as low as 350 degrees Celsius. So we can access those lower temperatures as well. And now we de-risk the idea. So we do a proof of concept. And now we're moving on. I'll show you, you get sort of a sneak peek here. So this is the first time I've actually shown this to anybody outside of Xterra. So it just so happened we finished the design this week. So that's why you're the first. And this is what we're calling our Gen 2 prototype. And so this one we're moving towards the pilot scale because we've got an upcoming pilot project that I'll talk a little more about. And the goal here is we want this unit to be sized for a 1 to 2 kilowatt size power. And to give you a sense of scale, this bottom surface, these edges here are about 16 inches wide. And so we've got a nice package here. As we mount this, we'll encase it in a solid case. I haven't shown that, so you can sort of see the inner workings here. And what happens is this unit essentially gets mounted directly on an exhaust line. So our first applications are going to be waste heat facilities where the exhaust line has the heat in them. So we can mount directly exactly on the side of that. And this bottom plate is our heat transfer surface. So all the hot air passing over it will transfer into the engine that way. And then we can capture the waste heat and convert it to electricity by hooking this shaft up to a generator. So a little bit more about how it works. You can see that we can mount it directly on the exhaust line and produce electricity. We're working with a steel mill. And one of the things they said to us at one of our early meetings was, this technology excites us so much because it's very difficult to move heat around, but it's really easy to move electricity around. So if you can install these things where the heat's produced, capture it there, do the conversion to electricity right there, moving it around the facility becomes really straightforward. And so the big things about our technology is that it's scalable. So we don't have to be big to be efficient. We can be efficient when we're small. And then what we do is we scale like traditional engines do, where we can use bigger pistons and more of them. So we have an extremely scalable package. And the second thing is we can install them right on the exhaust line. We don't need some of the other systems like the steam turbines or the organic Rankine cycle. They need a boiler, right? And they need other equipment. They need heat exchangers. Whereas we have this advantage where we can be installed right on the exhaust line itself. So this is our first pilot project. This is a picture of us at Gerdau's facility. So Gerdau is a steel producer, and the plant that we've actually been looking at two of their steel mills. One's in Whitby, which is nearby, which is nice, and the other one's out in Cambridge. A little farther drive, but a lot of opportunities there at both of those sites. And so we have a paid pilot project lined up. We're planning to install it this coming August of this year. And Gerdau is a really great partner. They've come on board very strongly, and they're really feeling this because they've electrified their facility. They have a strong need, and they have an enormous amount of waste heat. So they're sending multiple megawatts out this single exhaust line off the back of a furnace. So we can come in there and convert even a small amount of that. It's potentially massive savings for them. And it also counts as carbon reduction as well, because if the electricity that they need to make is done by either diesel or natural gas, we're offsetting that and saving them carbon as well. So we save them costs, and then we also save carbon emissions. We've talked to cement as well. As I mentioned, we're heat source agnostic. We can use anything, right? So, there's a couple others, solar thermal, geothermal, they've been talking to us as well. Nuclear is an interesting one too. So nuclear is trying to scale down their reactors. And so what's happening there is they're finding steam doesn't scale down. And so they've been reaching out to us as well and saying, hey, ultimately a nuclear reactor is just a heat source. So they need a way to convert that heat into power. So this is a tour that I did at the Lafarge facility. That's myself. That's Cody giving the tour there. And there's a lot of potential in cement as well, because off the back of the kiln, essentially the heat just comes right off a riser, and they're in the range of about 450 to 500 degrees Celsius, which is what we're targeting. And because we're scalable too, there's a nice application fit here. So there's potential we could in the future look for more pilots or projects in cement factories. Oil and gas is another one. Particularly, we're looking at compressor engines and compressor stations. So as they compress this natural gas, they'll exhaust heat that's in this sort of also 450 to 500 degrees Celsius range. So that seems to be a sweet spot for these industries. Steel, the reason we're at steel right now is because their exhaust line maxes out at 800 degrees Celsius, and the coldest it ever gets is 420. So for us, from a first application standpoint, that is an incredibly valuable heat source. That's high to medium grade heat right there that they're not using at all. So oil and gas is the 450 to 500 range. So there's potential applications there as well. And we'd offset natural gas. So there's direct carbon savings. Biomass is another really, really interesting one for us. So this is a tour that I did actually at wastewater treatment facility, and they have a lot of biomass as well. You're probably familiar with what that biomass comes from, but yeah, so they take all the sewage, and process it, and so we end up with a lot of biomass. And they've found certain ways to use it, but the Stirling engine could come in as a very effective way to use that and very clean. Also, the Durham York Energy Center. This gentleman was from there, and they also convert waste. So they have potentially a waste site where you can burn the waste. It's also very high energy, and so that's another way to potentially cleanly convert some of these waste streams into electricity. Biomass itself, when we look around, a big problem with biomass is sometimes they have to burn it because if you let it rot, it turns into methane, which is much worse for the environment, or they have to pay other people to come and take it away. And so you end up with they have all this biomass that they can't really do anything with, but it's costing them money. So we could come in there and say, hey, we can convert this instead of just burning it, make electricity out of it, right? And so there's huge potential in some of these industries to interface with them. And so that's what we're exploring now. So we've got this first pilot lined up, and we're out there, we're raising some funds for the company, and we're also looking for partners who can come in and partner with us with potentially like these medium to high grade heat sources. So they'll be great first applications for us for our technology. So in summary, sort of the take home message is there's a lot of waste heat and heat sources available that we're not tapping into right now. So I like to make people aware of this. If there are technologies out there, and hopefully our Stirling engine will be one of them, to capitalize on this massive amount of energy that's out there. Second point is, yeah, Xterra Stirling engines, we think they can get the job done. They can do clean, affordable, and reliable. And that's really what we're working towards at Xterra right now. And so we've got this pilot project lined up in August. So stay tuned for that. And of course, reach out if you have anything you want to share or any potential projects we should think about. We're very much open to that right now. So appreciate being invited to the Switch Talk. I'll stop there and see if there's any questions or turn it back over to David. Thanks so much. I really appreciate this.
Thank you ever so much, Brendan. That was very interesting. I'm going to start with one. I mean, there's some a significant number of Queen's and RMC faculty on the call, or former faculty, who probably can you explain a little bit more for those that might not understand this, exactly how the Stirling engine makes or uses the heat? Um, just to give everybody maybe a little bit more complete baseline.
Yeah, absolutely. So what you're trying to do in an engine cycle, right, is you're expanding air and compressing air, right? So what the Stirling engine does in the displacer chamber is it keeps one side hot perpetually and one side cold perpetually, right? And then it just uses the displacer to shift the gas between the hot chamber and the cold chamber. So what you need to do is when the gas is hot, you have to expand. And that expansion pushes the power piston and gives you your work. Okay. Then as the piston swings around, it has no choice but to compress the gas that's in there. Okay. So you need to make sure that the gas is cold when it's compressed, because when the gas is hot, it has more energy. So if you expand when it has more energy and compress when it's cold and has less energy, you get a net work output. And so to really do the Stirling cycle, you have to do all your expansion when it's hot, all your compression when it's cold, which is why you can't continuously be moving that displacer. And that's what we figured out. So our technology not only has the ability to dwell, meaning we can pause the displacer, but we can also control how it moves, right? And the regenerators that are in there are actually storing, as it goes between hot and cold, they're storing that energy, as I mentioned. So it's actually a fairly simple mechanical system. And then that shaft output, you hook it up to whatever you want, could be a pump or a generator or whatever, and that's the work output.
Right. A quick sort of corollary to that. How close to the theoretical have you gotten? Or
Yeah,
is that trade secret?
well, I showed the plot there.
Yeah, it looks
And
amazing.
and it looks pretty good, right? Yeah. So one of the things we're doing that we've patented the technology to control the motion, but The exact path that we follow is a trade secret. So we're creating these really complex splines now to jack up the efficiency. That benchtop unit was capable of hitting 4% just as a first effort, which is pretty good because we have no insulation on it. We have no thermal isolation. And we think our next unit's going to be easily 10% just when we turn it on. And that's kind of the range we'd need to make the pilot make sense for us. And then we start to pull up into potentially we can get 20 or 30% as we tweak the pathways on that cycle. We can pull it closer and closer to the Stirling engine because, yeah, I won't give too much away because that's a trade
Okay.
secret, but
Yeah, yeah, yeah.
you know, pretty close, pretty
All
close.
righty. Anybody on, there's one question in the chat. Paul McClatchy is asking any potential to use methane flares as a heat source.
Definitely. Absolutely. Yeah. Yeah. 100%. They're actually flaring. So the wastewater treatment facility I was at, they actually flare some of their biogas because that's the problem with biogas is it's methane basically. And if
Hmm.
any of that leaks, it's at least 20 times worse than the CO2 would have been. So I have to be
Yeah.
very careful with that. So yeah, flares is definitely one of the things we're looking at. That's a great question.
Wicked. Anybody else? I don't want to hog the conversation. Dave Lazell.
Yeah, this is very exciting, Brendan. I think this is fantastic. There was a company, I remember doing a bit of work with about 15 years ago with a New Zealand company called, I think it was Whisper Gen or something like that. And I'm afraid they went out of business. But what I guess I would love, I mean, one of the challenges has been how do you get, how do you keep it clean enough to get the resistance? And I guess it was some of the challenges I think were there is just that there's a fairly high maintenance cost to keep it clean, to get your all of the moving parts so they didn't bog down and use up all your energy in transition. So I'm quite interested in, it's like very exciting to see you're doing it. I love the idea of changing the wheel shape, to actually to get different power. It's a brilliant way of approach. But I guess I'm interested in what have you learned from other companies? People have been trying to do Stirling engine. I have one of those when I used to lecture on this stuff. One of those things I put on a coffee cup, a little
Yeah.
Stirling engine like the, and it's really an exciting technology, but just getting it to work. Can you give us maybe some thoughts of lessons learned from previous efforts?
Absolutely. And yes is the answer to that question. So we definitely have explored them. So I'm familiar with WhisperGen. That I think was the one that they tried to do marine-based power at first, I believe. So they were looking at boats initially. And again, it was fossil fuels, right? So they were sort of have your camping stove or whatever and power your boat, right? Have the electricity you need. So what's interesting there is like their tech, because they were stuck operating sinusoidally, they ended up having much different problems than we have, right? And so in a lot of those cases, like the tricky thing is in an internal combustion engine, you really can't copy what they're doing because that chamber doesn't stay hot and it doesn't stay cold. It flips between the two. So when you have your ignition, it's hot and then you exhaust and then you pull in fresh air and you're cold, right? So we don't have that same design. It's completely different. So on our hot side, we stay hot.
No,
So
that's important. Yep.
right, exactly. So it means we can't really have oil in there because and we know from experience the oil will burn. And then once it burns, it gucks it up and you don't have the heat transfer you need, right? So actually what we do is we do our sealing up on the cold side, right? So our power pistons on the cold side, we do our seals on the cold side. So we have more material flexibility there, meaning we can use some of these self-lubricating seals that'll be impregnated with things like Teflon, right? And so
Oh, okay.
sealing becomes much easier for us. Also, we have this ability where if it leaks a little bit, we just have a highly filtered, I'll call it like it's just basically a valve that cracks at a certain pressure. So the pressure can never drop below atmospheric pressure because it'll always pull fresh air in to refresh itself. And we can keep that very clean and we want to keep it very dry as well. So the nice thing again about doing this in 2025 is desiccants are super easy to find to keep the air dry. That's a very well developed technology because air compressors that are non-lubricating use the same technology, right? Um, and also these cracking valves are really high functioning now, and it's just simple mechanical systems. So the beauty of this is we want it to actually be very low maintenance. Like that's what we're selling it as because without the lubricant in there, no spark plugs, no transmission, nothing like that. we're trying to keep everything very simple. So our seals are sliding seals, and our goal is to have at least a few years between each maintenance cycle, which we're de-risking right now, but that's the target.
Cool.
Wonderful. Wow.
Yeah,
Boy, it's exciting. I hope it's successful. Thank you.
thanks.
Alrighty, I saw Andrew Wilcox up next.
Yeah, interesting presentation, Brendan. I do a lot of work with district energy utilities in urban environments, so I'm relatively far away from those industrial processes that you're talking about. But one absolutely massive and really significant source of waste heat I have are data centers, and so I'm wondering what happens to the process as that temperature difference drops. If I have a data center that can output 100 degrees Celsius waste heat. If I don't care about the efficiency so much, if I've got a 500 megawatt data center and it's not 20% efficient anymore, but only 10 or only 5%, that's still, megawatts of power that I'm freeing up. So what happens to the process as the delta T drops?
Yes. Firstly, thanks for that question because whenever I present to investors, I always say every single time I present this, I get the data center question because that's where all the heat is now, and that's the topic area. So I can consistently say that truthfully now. And I'll share this plot actually because I think I know not everybody's a fan of plots, but it helps me explain this better. So we essentially have our temperature ratio plotted on this axis here. So the efficiency is dependent on temperature, which is what your question is about, right? So this is our hot temperature over our low temperature, right? So it's essentially the difference between the two that drives the engine. So as you come down lower and lower, you're dropping your hot temperature, right? Down towards that 300, 200, 100, and you have to follow this curve down. So this dash line would be the max efficiency that a Stirling cycle could hit if it was perfect, which obviously you're never going to hit, right? And so you can see as you start to get down in this range down here where you're colder and colder, now even a perfect engine could only be 35, 30% efficient. So right now with our current technology, we figure we can hit about 300. Even our benchtop unit was running at 350. So the goal, as we get that colder and colder, our addressable market grows, and we really want to hit that data center mark, of course, because they're also remote. A lot of them want to be remote, right? Which is where if we had a low maintenance technology, we could do it up there. There's one that reached out to us that said they had an alfalfa farm nearby that had biomass that we could burn as well. So we can use like whatever they have, right? So to answer your question, we're not getting down there yet, but the more efficient we get, the closer we can get to accessing down. And probably realistically, we won't go much below 200 with a cycle like ours. But we're trying to get down into that 200 window to open up those opportunities for us because, like you said, like they don't really care. We used to think we'd have to be 30% efficient for this to make sense. But once we run the financial projections, 7% for most applications is just fine. That's a payoff period that's well under 5 years. You know what I mean? And we're trying to hit 2 years for most applications. So yeah, does that answer your question? Hopefully that.
Yeah, it does. I mean, because if I've got 100 degrees Celsius heat coming off of chips, and for half of the year, let's say I've got ambient conditions of around 0,
Mhm.
I've got a huge ratio, so it should be quite efficient if I've got that 100-degree delta. It's really interesting. Thank you.
Yeah, thanks.
I'll get to Darko in a sec. There was a follow-up from Dave Lazell. Could you use a different carrier fluid to allow you to use lower temperature waste heat?
It's possible. Like organic Rankine cycle technology is essentially like a steam cycle, but they use an organic fluid, right? And so like typically that cycle is designed to go down there and use I think even 70 or 80 degrees Celsius. It's not very efficient, but because they have that organic fluid and they tend to have like multiple heat exchangers, right? To sort of take the heat and then move it somewhere else and then do a phase transfer, right? So I think that's where your question is coming from. It's if we could do the heat exchange interface, but it would be better to use an organic Rankine cycle in that situation. If we had to go and do that, that step loses us enough efficiency that it probably doesn't make sense for most applications unless there's a really high need, right? So that's where we feel right now. We don't know for sure, but that's what the modeling has basically shown us. So thanks for that. Yeah.
Okay. And Darko.
Yeah, I have two questions. One is when you talked about attaching it directly to exhaust lines in industrial I guess there's quite a bit of research to be done to have most efficient extraction of that heat. You cannot just rely on transfer from air to wall to
Mhm.
the piping, existing piping. You're probably having like an inserting some kind of heat exchanger section with extended surface. Is that roughly the way you approach it?
Correct. And the pilot doesn't need that because the line
Yeah.
has, I'll sort of give you the rough numbers. There's
Mhm.
about 5 megawatts of thermal energy in that line. And we're running a
Yes.
1 to 2 kilowatt engine. So we've done the math on, we've essentially the bottom of our engine is a flat steel plate, and we've run the
Mhm.
convection numbers. There's
Hmm.
so much exhaust flying past there, and it's
Wow.
so hot. The convection's enough for right now. But if we want to pull, we're looking potentially, let's say we're 20% efficient on a 5 megawatt thermal energy line.
Mhm.
We could extract a megawatt out of that. But if we did that, we would have to run a heat exchanger across the tube and pull it more efficiently out of there. And we can look towards like what the steel mill does if they have enough space is they could run a recuperator, which
Mhm.
uses that type of like air heat exchanger system. So we
Yes.
can borrow that technology. It's not going to be new for us. It just means that like we do build in one slight level of inefficiency, but as I was talking about with Andrew's question, actually doesn't matter that we're inefficient because it's free energy.
Yes.
Right. So like
Well
all we have to
said.
do is pay back the installation costs. The CapEx and the OpEx is going to be so low. Right. So, you're right. Like when we're extracting the max limit on that, we'll probably have a heat exchanger across there and we'll optimize it. Absolutely. Yeah.
And just a second question was, it strikes me that there's still a bit of a competition in solar energy between EV panels and thermal solar, like with the heating tower. And in your case, that extraction from a heat tower would be so much simpler
Mhm.
because you just illuminate that uh, hot plate.
Yep. Exactly right. And that's been the historical problem with the thermal concentration systems is cost and pulling out enough power, right? So they try to use a molten salt in the middle generally where they're focusing it. But then sort of what do you do with that? Run a steam cycle.
Yeah.
It has to be huge to be efficient. So that's definitely on our list to target. Yeah, and space applications as well, because that solar energy is coming in, and you have a delta T
Huh.
because the shaded side is cold, is much colder, right, than zero. And the hot side is up to, sort of 200. So there's a delta T we could use as well. So the list of applications is pretty broad. Yeah.
And just, sorry, one more follow-up question. Um, Knowing that Stirling engine is often used in laboratory in reverse mode, where you supply electricity to get cryogenic cooling, uh, I'm just thinking, would there be some kind of sort of heat pump analog where you would actually use electricity to extract cold energy from outside?
Absolutely. And that's another area where right now they're struggling because a lot of the industrial heating is done with natural gas, right? And so if we do want to decarbonize these things, we need other solutions. So that's definitely on our list. Also long term, like there is the there is the consumer side of things. Like I have an off-grid cottage. I would love to just use my stack of wood to charge my batteries, right? Like that's the dream, right? So, and if I could then turn around and run it as a heat pump, right? On really, where the wood stoves maybe not cutting it, or I want to just be a little more efficient. You know what I mean? There's an opportunity
Yeah,
there as well to
absolutely.
interface because like you can run it both ways. It's completely reversible, right? Yeah.
Thanks.
Yeah.
All right. See Tom with his hand up.
Yes, I think we've got to keep in mind that the formula of T hot over T cold involves absolute temperature. Because if you're working in Celsius, if you have 100 degrees C waste heat and zero cold side, of course, you have infinite efficiency.
Mhm.
So there's a factor of 273 degrees there, I think.
Yeah. Yeah. 373 over 273 is the ratio. Yeah, exactly right. Yeah. Yeah, 0 Kelvin would be the perfect point, of course. But and infinite TH, right? TH as big as you want. So
To your point about space, because the cold side is pretty darn cold.
Pretty cold. Yeah. The colder the better. Exactly. Two ways
Yeah.
to pull that efficiency up. You go really cold, you go really hot. Yeah. Yeah.
Anything else from the floor? I have a business question. How many are on your team now? Because you've got, seems like the sky's the limit on opportunities.
Yeah, so three full-time employees. The pre-seed round, we're a hardware company, so we had to raise pretty early. So we don't want to raise too much funds in our pre-seed when the valuation cap, because we're raising on a safe, right? So yeah, so we have three full-time employees, and I could cherry pick because I'm a professor as well. So I picked people who are engineers, but also machinists. So we have some incredible capabilities on our team. I'll put it that way. So they're also the people designing it are also the ones making it and building it and testing it, right? So it's worked out very well for us so far.
Yeah. Well, I'm with a 12-year-old startup that has about 4.5 people. So I hope you get to market earlier
Thank
than
you.
we did.
Thanks. Yeah. Well, the pilot's going to be important, right? Because
Oh, exactly. Yeah.
that's what showed. Yeah.
Proof of
Awesome.
concept. Yeah.
Thanks. Thanks.
Alrighty. Anything else? No, I'm not seeing any other hands up or anything in the chat. So, Brendan, thank you ever so much. If you want to stick around, we usually do. We're ahead of schedule today, so that is great. Thank you for keeping it concise. As I said, we typically do a section on sector news at this point. Maybe I'll keep my politically charged question to the end. So I'm just going to go down the list and then we can jump in on anything because it seems going through the list in detail is not very efficient these days. Speaking of Stirling engines, and then trying to improve that. Electricity, fuel cells, solar, storage, bioenergy, EVs, transportation, wind, geothermal, water power, education, other. So if anybody has anything in those, any of those or anything else that you would like to bring up. No, I flagged this at the beginning when I was talking with Brendan and Darko. My question to the group, if you want to jump in, if not, that's fine. What is going to be the impact of Trump leaving most green transition programs around the world? What is Canada going to have to do to step up and continue to work with like-minded partners? Anybody got any thoughts on that, or is that too much for a Friday morning? Darko.
Uh, I would I would address that question in a month or two.
Okay.
I think the landscape is changing so much that it's like, how do we fortify buildings when it's in the middle of an earthquake? It's not a time particularly. Let it, because I mean, it's
Yeah,
really a daily sort of
yeah,
shifting terrain to use
yeah.
the earthquake metaphor. So, anyways,
Anyway,
I'm deeply concerned, but then I'm saving my energy for battles that we can fight. At this point, it's a tsunami that we just have to survive.
yeah.
That's how I see it personally.
No, and there's more than enough battles that we can, chip away at that will make a difference. Anyway, just that proverb
Sorry,
of may you live in interesting times.
one thought is that from part of that Engineers for Social Justice and Peace network and so on, and people mainly in the US, I can see that there is a tendency of people in the US to self-organize a little more than in Canada. We rely more on government policies and influencing those. In the US, I guess they've been experiencing historically far less strategy from the top down and far more self-organizing from the bottom up. But that's just my opinion.
Yeah. I mean, to the point that, some very Republican states are all in on wind turbines and other technologies because there's economic benefit, which seems to drive a lot of their, well, as it should drive their decision making. Dave Lazell.
Yeah, I think one thing that I certainly see happening, I think we all see it, is the possibility of more pipelines, and that will move, either oil from Alberta to the West Coast to Tidewater, or taking one of the natural gas pipelines across northern Ontario and converting it to oil, sort of the energy east. Especially if, and I'd say when maybe, the Americans take and shut off the oil pipeline through Michigan to Sarnia. And I think when, I suspect this trade war is going to get a lot worse before it gets better. And the impact on Ontario and on the Sarnia region for if the oil supply from Western Canada dries up, or they actually decide to tariff the oil coming into Canada, Canada's oil coming back into Canada. It's an interesting. You could say, well, they can't do that. It's not, well, they can. And so, and in fact, as we know, the governor of Michigan wanted to shut down that pipeline, one of the pipelines across. So I think that Canada's energy security is going to need to get that Energy East pipeline. I was surprised it wasn't built 5 years ago. And I think that within 6 months, we'll be seeing that back on the tables and a pretty high priority. But that is going to set us back. But I think the opportunity, I think, especially if the automobile industry is really, what Trump is doing is I don't think he's ever going to put a tax on Canadian auto parts coming to the United States. It'll hurt the United States too much. But he'll threaten it and just delay it every month. And his message to all the companies and the American companies is find suppliers in the United States, and shut down your agreements with Canadian suppliers. And because there's too much risk that he's going to one day put it on. We could start partnering with Chinese companies, electric companies, and maybe move faster to electric vehicles. But I don't know. It's an interesting,
fraught
gonna
with
be a
issues,
rough
that
road
one too.
between now and the next 3 or 4 years.
Anyway, thank you, David, for your thoughts. Anybody else? But if there's nothing in any of the sector news, or we try and, people bring up topics, what do we got? Rosemary Helmer. Rosemary, we didn't catch you at the beginning. Thank you for joining. Europe seems to have an appetite for LNG. How can Canada pivot to rapidly supply that need to replace sales from other sources in the US? Very, very good question. There's certainly been a lot of people questioning why we didn't go forward with that. Politics at the time probably played a large role. But I think, the political winds have shifted significantly on all those questions. So, yes, I've been hearing political commentators saying time to revisit. I don't have anything more technical than that to bring to the conversation. But very good point. Thank you, Rosemary. Anything else? In that case, we will let Brendan get back to teaching, being a CEO, being a tech entrepreneur, all those many, many hats. Thank you again ever so much for the presentation. Very interesting to hear what you're doing, and very pleased that Switch can support you getting the word out a little bit more. I think from the Kingston people, City of Kingston people that are on the call, you might be getting a call later on applications that they might have. So that's what the Switch is all about. And with that, I'm going to say that our next meeting is April 4th, and we've lined up a session on District Energy, and the details will be coming out in the email and social media blasts closer to the event. And I also want to say that our annual general meeting is in May, and we do need as many who have memberships out for that as possible. We need quorum so that we can go through the financials for the last year and all those other necessary but rather boring items. So please mark that in your calendars to attend so that we can proceed with the business of Switch. With that, Brendan, again, thank you very much. Thank you everybody for joining today, and we'll hopefully see everybody in a month.